All right, so here we go with section 2.7, inverse functions. With me, Mr. Hain. All right, so inverse functions, what the heck are they? So inverse functions are really defined by the following. The composition of the function both ways, the f of the g of x, so f of the g of x is equal to just the variable x, and g of the f of x is equal to just the variable x. And in other words, when the fog of x equals x and the gof of x equals x, so the compositions of the functions equals just an x. So let's take a look at what that means. I'm gonna always just define functions for you when we're doing fog and gof, or f composed with g and g composed with f. So my f of x here is 4x minus 7. And my g of x here is x plus 7 over 4. So in order to check, what we're going to do is compose the functions both ways. So the f of the g of x, so here when I have the x in my f function, I'm going to put the entire g function, and then I'm going to simplify. I have these two 4's, so those two 4's do cancel, and that leaves me with x plus 7 minus 7, and 7 minus 7, of course, is 0, leaving me with a single solitary x. So the fog of x is equal to x. F composed with g of x is x. So in order to make sure that g is the inverse of f, the opposite must also be true. So the g composed with f of x, so here, where I have x and g, I put the entire f function, 4x minus 7, and then I start to simplify. I have minus 7 and plus 7 at the top when I can take the parentheses away. That, of course, leaves me with just 4x over 4, and the 4's cancel, leaving me with just the g composed with f of x is just the variable x. And, of course, this means g of x is the inverse of the f of x because both ways that we compose them, both the fog of x and the gof of x are equal to just an x. So by definition, the g of x is indeed the inverse of the f of x. Awesome. So let's take a look at how we find the inverse of a function. Now I know that I rarely give you guys just a rote steps to follow, but this is one of those times where it's important to make sure that we always know where we're going to find the inverse of a function. So the first step is to replace the symbol f of x with y, just the variable y. And then I'm going to switch x and y, their places. There's no mathematical reason for this. I'm just going to switch them. Some students have called it the magic step. The mathematical reason is I'm really just forcing the function, if we can solve it for y, to be the definition of an inverse. But that's really complicated, and it kind of is explained by us doing the problems. So more importantly, I just call this switching x and y. So step 3 is you solve for y. Very rarely is it not possible. I mean, I can definitely create functions where you cannot solve for y. Know that almost all of the homework questions, I think all of the homework questions I've assigned, it is possible to find the inverse. So keep working at it. I'll give you lots of examples in this video. So we're going to replace y with the symbol, this symbol here, which is literally the f to the negative 1 of x. When you see this symbol, you literally read it the inverse of the f of x. It just means you found the inverse of that function. So find the inverse. Let's get a look at an example. So the first step is already done here. I've replaced f of x, that symbol, with y, and then switch their places. So y is equal to 2x plus 7, and then I switch the place here. Step 2, as you see in the pink, kind of like a preview that popped out early, I switched x and y. Step 3, I'm going to solve for y. So I subtract 7 from each side, and that leaves me with 2y here. And then I divide both sides by 2. And of course that gives me step 3, the solved for y, which is x minus 7 over 2, is equal to just the variable y. And then I replace the y variable with the symbol f, the inverse of the f of x, or f to the negative 1, as some people say. This is the last time I'm going to say that. I'm always going to read this symbol now as the inverse of the f of x. Awesome. So that is our inverse of the function f. So the second example, Slightly different. This one has a cube in it, so let's walk through the steps. First, replace the symbol f of x with y. Next is the magic step. I switch x and y. Just the letters themselves, nothing else changes. And so then we're going to solve for y. So I'm going to add add 1 to each side, sorry. And then I have x plus 1 over here. Divide by 4, so that isolates my y variable as a cubed variable. To undo a cube, you take the cube root. And of course, when I take the cube root of y cubed, that just turns into simply y. So now I have y is equal to the cube root of x plus 1 over 4. And if I replace the variable y with the correct symbol, step 4 gives us the inverse. The inverse of the f of x is the cube root of x plus 1 over 4. So that's our second inverse example, and that's again to find an inverse of a cubic function. Simple cubic. So here's the third example. I want to find the inverse of the f of x where it's 3 over x minus 1. So first step, replace the f of x symbol with the variable y. Second step, again, switch those variables around, aka the magic step. And then let's begin solving for y. So I'm going to add 1 to each side. And then I have y in the denominator, and that's troubling. I don't like that. So if I have y in the denominator, in order to cancel that y or move it to the left side of the equation, I'm actually going to multiply the entire equation by y. And so when I distribute, y times x is xy, y times 1 is y, and then when I multiply times the fraction with y as the denominator, they cancel, it leaves me just 3. This is perfect. And a lot of people get weirded out because they're like, hey, Mr. Hain, like, seriously, man, now you have 2 y's. Well, that's fine because these terms actually share a y, so I can factor that y out. And I have x plus 1, so I have two quantities times each other, which means I can just divide by x plus 1 and cancel the x plus 1 on the same side as the y. So y is equal to 3 over x plus 1. And of course, once I've solved for it, then the last step is just to replace the symbol with the inverse of f of x. So I do have an inverse of f of x. It is 3 divided by x plus 1. And that's my third example, or an example where I have the x variable in the denominator of the original function. So let's talk about the vertical line test. So what the heck is a vertical line test? Okay, if a graph passes, then each x value only has one y value. And that means it is a function. So all I'm doing with a vertical line test, or VLT, is testing to see if a graph is a function. So let's take a look at some pass and fails. So if I'm looking at the green side on the left, I'm going to draw a line with my mouse, and as you see, anytime I draw a vertical line, I can only intersect one point on the graph. Alright, here also, when I draw a vertical line, even here it's just getting really close to touching twice. It's just touching once. So anytime I draw a vertical line on the second graph here below, it only goes through that graph one time. So that's why it passes the vertical line test. Sometimes it's easier to see when it fails, and here I see in the first blue graph example, if I draw a line right through here, and maybe you want to hold your pencil up to where I'm drawing the line on the screen, you'll see that the pencil touches twice. In fact, my mouse touches once here and then once again here. That means that graph fails the vertical line test. This is not a function, the first one here. And if you look here, anytime it passes here if I just draw one vertical line. But if it passes through the graph twice, and here we can actually see the y-axis is acting like a vertical line, and indeed the graph touches both here, oops, let's go back, and here, and so it fails the vertical line test. So both of the blue graphs fail because a vertical line will touch the graph in more than one spot. So that's why these fail, and the green ones pass, because any line that I draw vertically through the graph will only touch the graph once. And the same thing is true for the horizontal line test. It's is performed the same way, but what it means is if it passes, then each y value has only one x value. And the inverse of that graph is a function. So again, let's take a look at some pass and fails. Here I can draw horizontal lines like the x-axis and see that it would only cross through the graph once for the top red graph. For the bottom red graph, the same holds true, just like the x-axis is a horizontal line. If I move that x-axis up and down, you see that it would only cross through the graph once. If you want to hold your pencil horizontally and slide it upwards, you'll see that the red graphs only touch your pencil once as it moves upwards. And conversely, here on the orange side, if I hold my pencil horizontally like the x-axis, as soon as it touches more than one spot, again you see it here on the right and here on the left, it fails the horizontal line test. It only has to do it once. So if I look at the bottom orange graph, you'll see here it's passing the horizontal line test. But as soon as I get here, it touches twice. And indeed, you see here on the x-axis, it actually intersects the graph once, twice, 3 times. So it really does fail the horizontal line test. So the graphs here in orange, the inverse is not a function. Now all of these graphs pass the vertical line test, so they are functions, but the only ones whose inverse is a function is here in red. So let's put these all together. If you have a one-to-one function, it is only true if the graph passes both the horizontal and the vertical line test. So both the inverse and the original graphs are functions. So here, again, they have to pass both the vertical and the horizontal line test. And you see both of these graphs, if you move your pencil with the y-axis left and right, only touches once. And then again, with your pencil held horizontally, it would only touch once for the first graph here on the left. So it is 1-to-1 because it passes both the horizontal and vertical line test. And the same holds true for the second graph. It passes the vertical line test because it would only touch along the graph once. And it passes the horizontal line test because it would only pass or intersect the graph once, any horizontal line that we draw. So both of these functions, both the left and right graph, are not only functions, are not only their inverse functions, but these graphs are 1-to-1. Awesome. And that is inverse functions, section 2.7.